So remember in calculus, if we've got y, okay, that's our main function here, then dy, now too many people, you're not listening to me. I want you to listen to me. I said, have a go at it, now stop. Now let's tune in and let's do it. Okay, it's more important that you're listening to me when I'm talking rather than concentrating on what I'm saying, because then you're not taking anything that I say. Everything I say is important, so listen to what I'm saying. dy and dx is going to be the derivative. That means it's the rate of change of this function. And so here we have our first real life application of calculus. So this is the function we're given to begin with. Okay, this is the height of a tree. And it says pretty basically to begin with, find the height of the tree initially, so when time is 0, and then after 6 years. All right, so that just means put t is 0 into the equation and put t is 6 into the equation. I think that's probably what we've started with. And so one good thing is, like with a question like this, it's good to put it in your graph straight away, and then just g-solve those points. All right, don't waste your time chucking it into the calculator and finding out what's it going to be. Okay, just g-solve it straight off your calculator. So I'm going to press trace, and I'm interested when x is 0. We've got y is 0.08. .8031, so it's a 3 significant figures, that's 0.0803, and that's meters. And then after 6 years, we'll just press 6, 8.772, so 8.77 meters. Okay, discuss as t approaches infinity. So there's 2 ways we can do this, all right? We can just look at our calculator. All right, look at the graph we've got there, and we can trace along it. Trace is the F1 button. So if I press trace, and I go as x is getting larger and larger, what is y getting closer and closer and closer and closer towards? And the answer is 12. You can see y is at 11.9, almost recurring there. So as x approaches infinity, the height is approaching 12. Let's demonstrate that mathematically. So what we've got, remember this is the function, 12 on top of 1 plus 5, 1 plus e to the 5 take t. So if we imagine, let's put in a large number, like 1,000. We're going to have 12 on top of 1 plus e to the power of 5 take 1,000. That's minus 995. Okay, if I put 1,000 in there, this is what it's going to become, which is 12 on top of 1 plus. All right, now that's got a negative power, so we can express it as a fraction. But the point of this is that what we have here is 1 divided by e to the power of 995. Now that means 2.72 times 2.72 times 2.72, 995 times. So this is an astronomical number. This is a massive number. So we have 1 divided by a massive number. This whole thing is getting closer and closer and closer to 0. And so our height is approaching 12 divided by 1. Our height is approaching 12. So we can think about these things mathematically. We can use technology to support us. So let's answer the question. As t approaches infinity, h of t approaches 12 meters. Very good. Okay, so then we're asked in part C, at what rate is the tree growing initially, and at what rate is it growing after 2 years? So there's 2 ways we can answer this. Okay, what we can do is differentiate this equation and then put those values of t in. Okay, or again we can go to our graph. And I don't even need to sketch the derivative of my graph, because if you look on my calculator there, I've got the x value, I've got the y value, and I've got the dy and dx value. I've got that setting turned on my calculator. I have shown you guys that before, I can show you that again. It's just in shift menu, there's a derivative function. You can have that turned on and it'll pop up. So if I go to initially, top x is 0, the slope is 0.0797. So let's answer that. We're just using technology to support us here. At what rate is the tree growing initially? It's at 0.0797 and then we need a unit. Now the height of the tree is in meters, and the time we're talking about is in years. Initially, it's growing at 0.0797 meters per year. Okay. How about after 6 years? How fast is it growing? So when x is 6, we've got our rate of change is 2.359. So that's C part I and C part II.
It says 2 years.
Oh, 2, not 6. Thank you, Carla. So let's go for 2. So what we're finding here, by the way, this is h dash of 0. You're substituting t is 0 into the derivative equation. All right, and then we're finding h dash of 2. And we're just using our calculator to help us. And we've got 0.5421. So that's 0.542 meters per year. All right, so you'll often see me, particularly in statistics, it's probably where it's most pertinent, you'll see me writing 4 figures and then rounding to 3. Okay, and I will do it here, especially if we're dealing with numbers that have lots of decimal places. Okay, so we can use our calculator there. Part D, when is the tree growing at the fastest rate? Okay, when is it growing at its fastest rate? What does that mean? That means when is the rate of change a maximum? All right, so what I'm going to do is I'm going to sketch both graphs up here. Let's exit out, and I've got the derivative here ready to go. All right, so the red graph is the rate of change, and we can see the rate of change has some maximum. That's going to be when it's growing fastest. So we can G-solve that max on this one. And it's when x is 5, x is time, so when t is 5 years, the tree is growing fastest. Okay. Let's make an important connection here. What does that max on the derivative correspond with on the primary function?
The concave.
Correct. Point of inflection. Okay, so we can't see it very well. I might just zoom in a little bit. Let's just change that. Okay, see here we have a point of inflection at time is 5. That's where it transitions. I can exaggerate it here on the wall. Okay, that's where it transitions from being concave up to concave down. That's the main function. And if you look at the derivative function, it's like this, isn't it? That this is where the rate of change is greatest. And it makes sense as well. Like if you think, where on this curve is it steepest? That's going to be the steepest point. If you're pedaling a bike up a hill, that's where it's going to be hardest to get to the top. Because from there onwards, the slope starts to decrease. The slope goes down. It gets easier to climb after that point. Just ask Tess. Okay. Next question. So we've done that one completely using our calculator. Let's, this next one, we'll try and see if we can get through it without our calculator. So I'll clear the board. So in your test, it's going to be very clear when you can use your calculator. It's going to be very clear when you have to do things manually. All right, if it doesn't say anything, then you can use your calculator as much as you like. So we've got volume of water in a tank is, now, if you were to put this in your calculator as it is, all right, it's probably not going to graph it the way the question is asking it to. Really, the question should have brackets around here, and you absolutely need brackets around there when you put it in your calculator. A similar example, and this is just some calculator lessons, is if you're putting in sine pi x or something like that. Okay, if you put that in, that's going to be an error as well. You need to put brackets around what you're finding the sign of. Okay, so that's a similar example. This is some function, and this is what we're performing the function to. Now, with Lin laws, so just point out a connection. We'll revise that connection. We could express this as ln of 0.1 plus ln of t plus 0.5. Okay, we could separate them if we need to. Let's see. Let's have a go through the question and see what it does. How much water was in the tank initially? So we are going to need to use our calculator here because I don't know the log tables off the top of my head. So we're just finding v of 0. That means we're putting the number 0 into this equation here. It's going to be minus ln of 0.1 plus 0.1 times 0 plus 0.5. So it's minus ln of 0.05. And what's the volume in kilolitres? 2.995. All right, which is 3 significant figures. There's 3 kilolitres. Yeah. So 3 significant figures we should write like this. Okay, when is the tank fully empty? Okay, so if this is the volume in the tank and there's water leaking out of it, when is it empty? It's empty when the volume is 0. So that means we're trying to solve, so that was part A, here's part B. We're trying to solve when the volume equals 0. Okay, so we can start by getting rid of the negative, divide or multiply both sides by -1. Alright, and how do we get rid of ln? We put e to both sides. So we're going to have okay, another connection here. Now you might be inclined to, I've got 0.1 here, I want to get rid of that. I'm going to divide both sides by 0.1. But let's try and think about things a little bit differently. 0.1 is 1 divided by 10. And so the way we can get rid of that is multiply both sides by 10. All right, so in the next step, we're going to have t plus 0.5 equals 10. And then t equals 9.5. So what's the situation? We've got a tank, we've opened the valve, water's leaking out, the volume's changing. That's how much water was in initially. This is how long it takes till it's empty. 9.5 minutes. Hence, state an appropriate interval for the domain. So if we will have a look at the graph of this one, just to help us comprehend what's going on here. And by the way, when it says, in your test, when it says, doing things manually, you still use your calculator to support you. It just means you have to produce the calculations manually on the paper. So, like here, if I'm said we're doing this question manually, well, we can still look at our calculator and tell us how, absolutely. No one's checking to make sure you're not doing that. So we've got here minus ln bracket 0.1 bracket x plus 0.5 bracket. And unselect the derivative for now. So there it is, it's just going down, and I might just zoom out a little bit more. And for y we'll do that. Okay, there we go. So the point I'm trying to make here is this graph describes the volume of water in a tank. Okay? So I'll just sketch it here. It's like this, isn't it? Where that's 9.5. So for values of time greater than 9.5, what does it mean in the context of the problem? Now, this is volume. This is time.
Nothing's happening because it can't empty past 9.5.
Excellent. Okay, so here is where the tank is empty. So it started with 3 kilolitres, and then it starts emptying. Here it's empty, and so this here doesn't make any sense. It has no use to us. And so this model, remember this is a model, we're using this as a model, is only valid for values between 0 and 9.5. It doesn't make sense to talk about negative values of time, and it doesn't make sense to talk about values of time greater than 9.5. All models have their limitations, don't they? And this is the limit of this model that we've got here. Okay, what is the volume after 4 minutes? So we're finding V of 4. Have to get units. Okay, again, when we're answering a problem like this, okay, it doesn't make sense to leave your answer like that, does it? You know, how much volume is there? Oh, there's minus ln 0.45 kilolitres. Like, well, what is that? Okay, so you are going to need to evaluate that to 3 significant things. Part D, when is there 1 kilolitre of water in the tank? So we've already found when the tank is empty, that's when the volume is 0. When is there 1 kilolitre? Well, that's when V of t equals 1. Remember, the volume is minus ln of 0.1 t plus 0.5. Okay, when the volume equals 1. Okay, so same rules apply here. Now we could, if we're not told to find the exact value, all right, if this is a 1 mark question, we can go straight to our calculator and go G-solve. What is the x value when y is 1? Okay, and we've got there, when the time is 3.17 minutes, the volume is 1 kilolitre. All right, so that's fair enough. It may say find the time exactly. What does it say here in the question? When it doesn't, it's ambiguous. When is the 1 kilolitre? So let's find it exactly. And so what we're going to do, we'll shove that negative over the other side to begin with. All right, we'll put e to the power of both sides. E to the minus 1 is just 1 on e. Again, we've got that 0.1, so we just multiply both sides by 10. And then shove the 0.5 over. So that's it exactly, you know, and if you put in your calculator, well, what is 10 on e? 10 on e to the power of 1. So e by itself just is e to the power of 1. Take 0.5. 3.178. Which is 3.18 minutes. Okay, 3.18 minutes. Okay, which is 3 minutes. Okay, so sometimes you get asked questions like this. 3 minutes and 0.18 times 60. I apologise, I haven't, oh no, that's 3.178, so that's fine, yeah, 3.18, and then 0.18 times 60, we've got 10 and 10.8 seconds. Right, so we might be asked to write it in how many minutes and seconds is that? Alright, so we expect you to be able to convert, oh well, take the 3 minutes there, and the 0.18 is 0.18 minutes. How many seconds is that? Okay, so we found it exactly, and then this is the value to 3 significant figures, and that's the value that we were able to G-solve as well. Notice up there, I said when y is 1, what's the value of x? 3.18. Excellent. Okay, what's the next part say? What rate is water leaving the tank initially, and when time is 0? What rate is it leaving initially, and when time is 0? So let's do this part manually. Okay, rather than relying on our calculator. Again, we could just G-solve from our graph here, but we didn't do it with the first one, so let's do it with this one. Any objections if we write this out? So, this is our function, and if we want to know the rates with it, we need to find V dash. Okay, now you could expand this and differentiate it. Okay, but I suspect it's going to be easier to split it. All right, like I said, we could do right at the start. I suspect it's going to be easier to split it. Okay, so then what it is? It's negative ln of 0.1. Take ln of t times t plus 0.5. Okay, so that's still v of t, and then when we're going to differentiate it, it's just going to be one step. It's going to be nice and easy. This is a number, okay, minus ln of 0.1. There's no variable involved in that, so when you differentiate that, that's just going to 0. That disappears, so we don't really need to worry about that, and then we're just looking at this part. The negative's just going to hang out there, so we can ignore that, and then we're just differentiating ln of t plus 0.5. Well, remember, if we have ln of f of x, the derivative is going to be f dash of x on top of f of x. So the derivative of what's inside brackets, it's t plus 0.5, is just 1, and then at the bottom, t plus 0.5. Okay, so that's our derivative function. What rate is water leaving the tank initially? So that means finding v dash of 0. Minus 2 kilolitres per minute. All right, so initially it's coming out pretty fast. Open up that valve. And of course that makes sense, right? Because there's more pressure in the tank, there's more weight, and so it's got more force pushing it out the valve at the bottom. Okay, what about when time is 6? So v dash of 6 on 6 plus 0.5. And we get that to 3 significant figures. Okay, so look at this. At first, it is gushing out the tank, right? And then after 6 minutes, it slows down. It's only coming out at 154 kilolitres per minute. Sorry, 154 litres, 0.154 kilolitres. Okay, last part. When is water leaving the tank at the highest rate? Okay, so there's a couple of ways we could do this. So it's when is the rate of change greatest? So I think the most sensible way is to just look at the derivative. All right, so let's graph the derivative function. And what I might even do is I'll just get rid of the initial function as well. Okay, what I want you to notice is this describes the rate at which water is leaking out the tank. So it helps if I can point at it, so I'll do it like this. Okay, so initially, right here, and remember it's only valid, remember the initial function is only valid until time is 9.5. And so that means the same case applies for the derivative. It doesn't make sense to say, what's the rate of change at 10 minutes? Well, there's no volume in the tank at 10 minutes. The function's obsolete. This is where the rate of change starts. Initially, it's minus 2 kilolitres. That means water's coming out at minus 2 kilolitres. And what we can see looking at it is that the rate of change constantly gets slower and slower and slower. Water comes out at a slower and slower rate. Okay? So what this means is the heaviest flow rate is initially. And this makes sense in the context of the problem. That's when there's the most water in the tank. So to answer that, that's part F. When T is 0, flow rate is greatest. Okay. The other thing, right, is remember I've said on the previous example we saw a point of inflection on the initial function, all right, and the point of inflection was when the rate of change was greatest. If we look at the function here, the initial function here, and I'll unselect that one, there is no point of inflection. Okay, it is concave up for all values of x. So because there's no point of inflection, all right, remember point of inflection on f of x corresponds with turning points on f of x is going to be roots on f dash dash of x. All right, so that was it. That was one relationship we've recognised. Now there's no points of inflection on f of x, which means there's no maximum or minimum flow rate. All right, so then we're just saying, well, when is it at its greatest value? All right, it's always negative. It's always coming out. Here is when it's at its greatest value. All right, that's enough. So that's enough to get into 3F, and that's what we're going to have a crack at today. I've also got, for homework tonight, another one of those graphing questions. So remember we've said those relationships between graphing, f of x, f dash of x, f dash dash of x. So this is from last year's exam. Okay, this was probably one of the trickiest ones I've seen in a while. So take it home, have a go at it, and I'll put a solution up for you guys tonight. All right, mate, good chat. Cool, so 3F, let's get into it.